Hello, I'm Sam Ainsworth, and this is my short talk on ParaDox, our new technique designed to improve performance and/or power consumption by replacing the excessive margins on chip supply voltages, which typically waste over 20% of a CPU's power but are there to avoid errors from variance and unreliable physical properties, with real efficient fault tolerance. Because the latest fault tolerance techniques, based around exploiting the parallel nature of fault tolerance, are so efficient, there becomes the potential to improve in multiple dimensions of energy, performance, and reliability all at once. So first, why is this now a realistic possibility? Why is the full fault tolerance of today's processors, designed to check for bit flips and incorrect computation caused by cosmic rays or timing errors, now achievable in such an efficient way that it can be more than paid for by a reduction from voltage margins? Certainly, dual and triple core lockstep, which duplicate all hardware logic and compare the results, are nowhere near efficient for such a proposition. But who said we have to run a fault-tolerant, redundant copy of the program in the same way as the initial run? Actually, it turns out that error detection is extremely parallel, even for single-threaded applications. We can split up our program into multiple segments, writing the performed loads and stores into a log to be replayed, then checking the results on a much slower, much more energy efficient checker core. While that part of the code is being checked, we can immediately log the loads and stores of the next part of the program, overlap its checking with the first segment on a different, slow but efficient checker core, and so on and so on. Critically, this type of parallelism doesn't affect coverage. We still repeat all execution, just in a different, more parallel way for the redundant run. And we can combine the results from each separate check using an induction-style analysis. If all segments previous to ours are correct, and our current segment is as well, then the entire program up to this point must have been executed without error. We used this property in a paper at DSN 2018 by coupling a standard out-of-order CPU with hardware forwarding logic to forward and check values from the first execution. These slices of the program between register checkpoints are repeated on tiny checker cores. Then, to make the induction process work, we check that the register checkpoints recomputed match the ones taken from the next checkpoint. At DSN 2019, we then extended this error detection scheme to allow it to correct any faults by buffering all store values to allow rollback under the discovery of an error, and buffering errors at the L1 for multicore correctness. There are more details in those two papers, but the fundamental takeaway is this. Via exploiting parallelism in fault-tolerant repetition, we can reduce fault-tolerant overheads to be almost negligible on performance and power consumption. If full fault tolerance is now incredibly cheap, how does that impact microarchitectural design more generally? To limit the impact of variance in today's chips, supply voltages have to be set significantly higher than is strictly necessary, and a great deal of circuitry and effort has to be spent on other power-related sources of error, such as voltage spikes. If this limited form of error mitigation, of over-margining the voltage supply, is so costly, and full fault tolerance is cheaper, then why don't we just go for the latter instead? That way, we could undervolt the design to achieve better energy consumption, or overclock it to improve performance, with any errors corrected by the underlying fault tolerance. Well, as it turns out, in error-seeking scenarios, unlike in typical error-free execution, the rollback cost of ParaMedic is a significant concern. Once errors become very common, we see slowdowns increasing exponentially, reaching up to 16x on the graph above. Ultimately, if errors are relatively common, and the success of each checkpoint depends on the correct execution of thousands of instructions, then forward progress is likely to be limited. Still, knowing that this is a problem, ParaDox, our new scheme, does something about it. In fact, ParaDox gives comparable performance to ParaMedic at around 1.5 orders of magnitude higher errors. How do we achieve this? We reduce the cost of this rollback using a variety of methods, both to limit the wasted computation and the time spent undoing incorrect writes. We use a dynamic scheduling technique to adapt the number of instructions being checked and thus needing to be rolled back at once. We also dynamically adapt voltage to moderate how error-seeking we are at any one point, redesign the rollback mechanism to take account of spatial and temporal locality, and reschedule the use of checker cores to better facilitate power gating. Once the scale of undervolting possible on modern cores is taken into account, the power savings of ParaDox stand at 22%, even including the extra cost of the error checking. Though the slowdowns on some workloads caused by the checker cores not keeping up, the multicore correctness mechanism and the errors themselves mean that the EDP win is not always net positive. The geomean saving on energy delay product is 15%. Alternatively, if we increase clock frequency to counteract the slowdown, we would still save 15% on power consumption. And if we were instead to overclock the design to improve performance, we could increase clock frequency by 13% while using a small undervolt to keep power consumption constant with the baseline. Today's margins are too big to remain the solution for keeping hardware running, and the potential savings make new techniques a necessity. Instead, we think that better consideration of fault-tolerant designs and trade-offs in the space of reliability and performance allow improvements along multiple dimensions at once. Thank you for listening, and I'm happy to take any questions.